Good afternoon, Internet. I am Matt Booyak, and in this video we'll be taking a look at the 53rd problem from the Project Euler Problem Archive. Now, this problem asks us a question about the binomial coefficients, and in particular, it asks us to find the number of binomial coefficients with n less than or equal to 100 that are greater than 1 million. Now, if you aren't familiar with the binomial coefficients, you might recognize them from Pascal's triangle. The idea of Pascal's triangle is that each row in the triangle, if you take two adjacent numbers and add them, you're going to get the number between them in the next row. And these correspond, as I said, exactly to the binomial coefficients. These show up in probability, combinatorics, and many other subjects in discrete math, but we actually don't need to know any of that in order to solve our problem. We just need to know this expression here. This is often abbreviated using this notation, which is pronounced n choose r. And the reason we say it like that is because it corresponds to the number of ways to choose r items from a set of n items. It gives this example: if we have 5 digits and we want to choose 3 of them, there are 10 ways to do that. And if we were to put 5 and 3 into this equation here, we would get 10. And you can see there are, in fact, 10 ways of doing it. One thing to note is that we see 1, 2, 3 in this list. We don't see 2, 1, 3 or 3, 2, 1 or any of the other permutations of 1, 2, and 3. And that's because it's not the particular order of the items that's important. It's just the set of items that we're counting. But as I said, we don't actually need to know any of that. We just need this expression right here. So the most straightforward approach to this problem is probably just to calculate the binomial coefficients for n less than or equal to 100 and r less than or equal to n, and see how many of them are greater than 1 million. The problem starts with this term here, n factorial, which grows incredibly quickly. Even for this coefficient here, 23 choose 10, you're going to have to compute 23 factorial. So even though this number is quite modest, just over 1 million, you would have to calculate some very large numbers if you're going to use this expression directly. But you might think maybe we can come up with some more clever approach to calculating the coefficients that doesn't actually involve calculating n factorial. Well, I've got some bad news for you. We're still going to be in trouble. Let me show you an example. The biggest binomial coefficient we would have to compute in order to use the approach that I just described is going to be 100 factorial divided by 50 factorial squared. And that gives us this monstrosity here. If you're curious, a way that you can check to see if a number will fit in a 32-bit or 64-bit unsigned integer is just to take the log and then divide that by the log of 2. That will give you the log base 2. And you can see it is way larger than 63 or 31. This will not fit in any of our native integer types. Now, we do have a big integer class that we wrote a little while back, and we could use that to actually calculate all of the binomial coefficients that we need to. But usually, if you can avoid using the big integer class, that's better, because as you get to calculating these very large numbers, the big integer class does tend to slow down. It's very powerful, but you can't get around the fact that these numbers are just really big. Okay, so how are we going to tackle this? Well, instead of calculating these monstrously large numbers, it might be easier to find out how many of these numbers are less than or equal to 1 million instead of calculating how many are greater than 1 million. After all, we know the total number of coefficients. We can just calculate the number that are less than or equal to 1 million, subtract that from the total number, and that will give us the number that are greater than 1 million. Now, I want to take another look at Pascal's triangle so you can get some amount of intuitive understanding about how these numbers behave. So for a given value of n, we're going to be looking at a particular row of the triangle. So if n equals 0, we're going to be looking at the top row. If n equals 1, we're going to be looking at the next row. And if n equals 2, we're going to be looking at the next row after that, and so on. You'll know it's kind of off by 1, where the top row does not correspond to n equals 1. It corresponds to n equals 0. And then within a particular row, R is going to give us the element within that row that we're interested in, again, starting with 0. So if we look at the example that they give with 5, choose 3, let's see if we can work that out. So count 0, 1, 2, 3, 4, 5, and then we count 0, 1, 2, 3, and that gives us 10, which is exactly as we expected. But more generally, I want you to take a look at how these numbers seem to behave. We can see that they always start with 1 on the far left and the far right, and they increase to some maximum value in the center, and it's symmetric left to right. And so what we can do is scan along a particular row until we come to a number that's greater than 1 million. Then in order to know the total number of coefficients in that row that are greater than 1 million, we'll take the number that are less than or equal to 1 million, double that, subtract that from the size of the row, and that will give us the number of coefficients greater than 1 million. You'll notice that the number of elements in each row is 1 more than n. So when n equals 0, there's 1 element. When n equals 1, there are 2 elements, and so on. Okay, so now the only thing we really need is a way to efficiently scan along a row of Pascal's triangle. Ideally, we would have some technique for computing n choose r plus 1 given n choose r. And so that's the first thing we'll look at. Before we write some code, we'll have to do some analysis to derive that. And so let's get into it. As usual, we will copy our template directory to make our problem directory. Enter our problem directory, and open our main.cpp. And by that I mean we'll open our analysis file. As I said, we'll need to do some thinking first. So just to copy over from the problem description, the expression that we have for the binomial coefficients is going to be n factorial over r factorial times n minus r factorial. Just like that. And what we would really like to do is to determine an expression for this, n choose r plus 1. Okay, well we can just take r plus 1 and substitute it into this expression here and see what we get. Well, this is going to end up with a minus 1, and this is going to be just r plus 1 factorial. Now, is there a way that we can write this expression in terms of this expression. Like, that is, how can we manipulate this expression so it looks a bit more like this one up here? And the first thing that we'll do is to multiply the top and bottom by n minus r. So let's do that. So here we'll say n minus r times n factorial. And multiplying these bottom terms by n minus r is going to turn this back into n minus r factorial. Then we can factor out an r plus 1 from this bottom term here. And what that's going to give us is n minus r over r plus 1 times this expression here. And you'll recognize that this is exactly what we started with up here. And so we can take this expression and replace this whole chunk by choose n comma r. And so this is exactly what I was describing, where we want a way to efficiently determine the next element in a row of Pascal's triangle from the one before it. And just to recall our base case, if we do choose n comma 1, that's just going to be n. I think it's not too difficult to see if you plug in 1 for r up here. Okay, so let's work through an example just so you can see what this is going to look like. So let's calculate the n equals 7 row of Pascal's triangle. So let's make a little table. R is going to go from 0, 1, 2, 3, 4, 5, 6, 7. And for each row, we want to compute choose n comma r. And to help us compute the next row, we want to calculate n minus r over r plus 1. Okay, so we're going to start off for the first row. We have n choose 0. Actually, this is perhaps a better way of defining our base case. You can either do it as n choose 1 is equal to n, or you can do n choose 0 is equal to 1. It's going to work out the same in either case. Okay, so that's going to be 1. Then here we have n minus 0 is just n, so that's 7, over r plus 1. R is 0, and so that's going to be 1. We multiply 7 over 1 by 1, and we get 7. So you can see this is exactly what I was talking about with being able to use either the r equals 0 case or the r equals 1 case as our base case. Okay, so now let's compute this value again. So 7 minus 1 is going to give us 6. Over 1 plus 1 is 2. And we could write this as 3. 6 over 2 is 3. But there's an advantage of writing it like this, because it helps us recognize that each time we iterate through this loop, the denominator is getting smaller by 1 as r increases, and the denominator is getting bigger by 1 as r increases. And so instead of having to go back and remember what is n and what is r, and let's compute n minus r, and let's compute r plus 1, you can just take the value here on this row and adjust it to get the next row. Let me show you what I mean. So this works out to 3. So this is going to be 21. Then for this row, we're going to take 6 and decrement it to get 5. And then we're going to take 2 and increment it to get 3. So then we have 5/3. And that's going to give us 35 over here. Continuing this, we're going to get 4 over 4. That's, again, just by decrementing the numerator and incrementing the denominator. So we have 35 again. Continuing, we have 3/5 gives us 21. 2 over 6 is going to give us 7. And finally, 1 over 7 is going to give us 1. This also helps to explain why the rows of the triangle end up being symmetric. You can see that these values down here are the same as these values up here. They're also symmetric. Okay, so this is going to be our technique to efficiently calculating the binomial coefficients. So now I think we are finally ready to write some code. Okay, so let's say for int n equals 1, n less than or equal to 100, increment n. But actually, we're not going to start at n equals 1. I was a bit hasty in typing that in here, because on a given row, we want to continue searching until we come to an element that is greater than 1 million. And that won't happen until we get to n equals 23. That was given to us in the problem description here. Our algorithm doesn't work as well for the rows before that because all of the values in all of those rows are less than 1 million. So we're going to start at n equals 23. Okay. Let's remember to keep track of our solution. So this is going to be the total number of coefficients greater than 1 million. Okay, and we're going to need our numerator and denominator. So we'll say int numerator is equal to n, and denominator is equal to 1. Let's just do a quick sanity check on that, going back to our analysis. So yes, for the first iteration, we're going to have the numerator is going to start off at n, as you can see, and the denominator is going to start off at 1. Okay, we'll also want to say int coef, our coefficient, is going to start off at 1. And we're going to count the number of coefficients that we find that are less than or equal to 1 million. Now this is a bit tricky because what we're going to want to do is actually start off with the count equal to 0. And that's because we're going to enter into our loop down here where we say coef less than or equal to 1 million. It's only once we enter this loop that we're going to increment. That way, on subsequent executions of the loop, we will only increment once we have verified that our coefficient is still less than 1 million. And so it's a little bit perhaps counterintuitive that we start at 0 instead of 1, but that's just the way it works out. Okay, so we're going to increment count. We're going to say coef is equal to coef times numerator divided by denominator. And I specifically did it this way instead of, for example, this way, because this is not guaranteed to be an integer. We're not working with floating point numbers here. These are integers. And so you can see here, for example, 5/3 does not divide evenly. And so we need to be careful to multiply the coefficient by the numerator first and then divide by the denominator. Okay, so we have our new coefficient. We're going to want to adjust our numerator and denominator. So we'll decrement the numerator and increment the denominator. You can see, going back to our example, that that's exactly what we did here. Okay. And it's at this point we will check that our coefficient is still less than or equal to 1 million, both for incrementing on subsequent iterations. Okay, so eventually we're going to find a coefficient greater than greater than 1 million, and then we'll break out of the loop. And now we need to calculate how many coefficients greater than 1 million are there based on the number of coefficients less than or equal to 1 million that we found. Remember, we need to double our count because the triangle is symmetric on the left and right. Going back to Pascal's triangle here, if we were trying to count the number of coefficients in this bottom row that are greater than 25, for example, we would count that there are 3 that are less than or equal to 25. We would double that to get 6, and we would subtract that from 8 to get the 2 coefficients greater than 25 here. Just using a smaller value to show an example that we can actually visualize, as opposed to talking about coefficients in the millions. Okay, so we're going to want to subtract that from the total number of coefficients in the row, which, as I mentioned, is just n plus 1. So we're going to say solution plus equals n plus 1 minus 2 times count. Okay. And then we're going to try the next value of n and continue until we get to n equals 100. And at that point, we should print out our solution. So we'll say printf, solution equals %d, solution. And we'll say make. I did not actually do this assignment correctly. And let's run the solver. We get 4,075 as our answer. So let's go back to the archive. I don't believe I even made an effort to sign in. No, I did not. So if you'll give me one moment. Okay. Now we can go to the second page, problem 53, and we see that the answer is indeed, getting rid of the calculator, 4,075, completed when dinosaurs roamed the earth. So as always, thank you very much for joining me. Tomorrow we'll be tackling problem number 54.